Alright everyone, welcome to week 11 of Advanced Digital, um, where we take a brief look at a plugin called Weaverbird. Weaverbird is a topological mesh editor, which means number one, it works more or less exclusively with meshes. There are actually a fair number of Grasshopper and Rhino plugins that deal with meshes or work with meshes exclusively. Weaverbird is simply one of the most popular ones. And if you click on the website, this is the website where you download the program or the plugin and just run it. It's an install file. It should be pretty straightforward to install. And because it works with topology, it basically means it kind of works, modifies, or edits essentially the layout of a mesh. And we'll take a look at that a little bit. But it works well in particular with the next plugin we're going to look at called Kangaroo. So we'll see how it's used in conjunction with that plugin. Reordering, and it's essentially kind of actually, you'll see preparing sort of complex mesh frameworks for 3D printing, because it does actually have a sort of mesh offset component with it as well. So that's an installation file. You can download it and install it on your own computers if you want to. And this is just a really quick example file. The first thing I'm actually going to look at is this, the Tessellate .3dm file. And this just kind of gives you a basic understanding of what Weaverbird will do in some cases. And it's the simple idea of, like, you can take a triangle, because meshes are always triangles, right? Mesh is basically a bag of triangles defined by 3 vertices. And then what it does is that it finds different ways, or it's basically a collection of different ways of reordering, resorting, rearranging, or re-subdividing a mesh triangle. So you see here the two main sort of most obvious methods. If you take the area centroid of a triangle and you draw lines to the vertices, this is what you get. You get one triangle split into 3 smaller triangles. There's a midpoint mode where you take the area centroid and you draw a line to the midpoint of the side, and what you end up is this sort of diamond-shaped quad, more or less, right? So between these two, you get a different result. And then you can actually mix and match. So you see, if I take vertex mode and then I do it again, this is what you get, and you do it again, this is what you get. And you'll see that this, as you kind of zoom in, after, let's say, 3 successive applications of the vertex mode, what you get is really skinny triangles, right? And for the most part, usually in a sort of mesh subdivision, unless this is explicitly what you want, people try to avoid really long and skinny triangles because they cause problems, especially if it's a curved surface. Then you'll get a sort of really flat face right there, especially if the curvature is going in this direction. So these are just examples of these different methods being mixed up, and the sort of results that you get are fairly different. And you can kind of basically understand Weaverbird as a set of algorithms that basically go through a similar process, and it's not as simple, but this is kind of like the simplest way to understand what it does, and visualize it for you. So if you go and open up this file, this Grasshopper file, what you should get, turn it on, is something like this. Now, you can ignore this. Most of this is just me doing the grid and kind of assigning the center points to each of these. Now this, after you've installed Weaverbird, you should get a Weaverbird tab, as the sort of plugin tab on its own. This is Kangaroo, which we'll eventually be looking at. But this is Weaverbird. And what I actually just did was I popped in one of these, Weaverbird polylines dodecahedrons. And there are actually some other ones you can look at, but this is just an easy starting point. It's a dodecahedron. That's what it looks like, 10-sided. You can specify a radius, which these I specified as 20, so they're larger. And then I specify a plane, which is like its starting point. Right? This is at 0, 0, 0 by default. I just move them around. Okay. So these are hidden, but you can turn them on by doing Control Q, and then they're there. So you see this outer frame is the original dodecahedron, and essentially, for the most part, at least initially, we're looking at all these guys. So these guys are sub-D, which are subdivision modifiers, essentially. Some of these other tools are for kind of extracting certain parts of mesh geometry to use, right, to do something with. So naked boundaries, vertices, face polylines, that sort of stuff. But right now what we're looking at is this. Now I actually kind of go roughly in order. So the first one is the Catmull-Clark subdivision. And you'll see that this is what it does. There are only a couple inputs, so the initial mesh or curves like that as a list, the level of subdivisions, and how you want to do naked edges. Now, because these are off of the sort of closed dodecahedron, none of these naked edges will actually do anything because we don't have any naked edges in this particular scenario. Right? So it doesn't matter. But if I highlight this, then you kind of see the sort of types of faces that you get. So it takes that sort of pentagon shape and sort of draws to the center, right? But you also see it gets an offset because it's sort of basically subdivided and relaxed. Now this is the subdivision iteration. So you see as I change it, it gets rounder and rounder and rounder. And usually it doesn't go past 3 iterations. 3 is generally the limit that is sort of suggested. But you see after 3 iterations, it actually gets really spherical, right? So this is actually the sort of subdivision modifiers are used kind of almost more or less explicitly for smoothing or relaxing of mesh geometry. Although you'll see that because of its method, you can still kind of see the original pentagon shape in there. Like there's this, which is still a pentagon, and these are all actually evenly divided quads. Okay, so this is actually a subdivision method that works pretty well for dividing surfaces into equally sort of mesh triangles or quads with roughly equivalent edge lengths, right? So like each of these edges are not hugely different from each other, which is great in many cases. Okay, so you don't get really skinny and long triangles, that sort of stuff. Okay, so let's move this back. And so these are sort of actually just one by one. So this one is the next. This is the split quads. And let's see. So the split quads actually does not necessarily relax it the same way this one does, right? The original dodecahedron is still actually really there. It only just subdivides the face. It doesn't actually relax it. Okay. Next one. These guys. This is the inner loop or inner polygons subdivision. So go back. So this is basically using the midpoints to kind of redraw a series of polygons, and each loop just successively gets smaller and smaller. Right? If I baked all 3, then they would all be sort of like circumscribing pentagons within each other. So It's really simple, easy to understand. Weaver loop, actually one of the commonly used one. WB loop is a very commonly used one. And same thing. All right, so you can actually get triangles instead of quads. Triangles are also relatively sized, so their edge lengths are pretty consistent. Okay. Sierpinski, this one. Okay, so from here to here, so it basically does a further level of subdivision, and then it kind of deletes out or hollows out that sort of center triangle. This is actually a fractal logic. Okay, and then the last one here is the split polygons. And you can always just you can play with this a little bit yourself just to kind of understand. If the original dodecahedron here is getting in your way of visualization, then just select them all, Control Q, turn them off. And then, okay. So this actually kind of constructs a mesh framework that's sort of denser along the original lines, and then it kind of gradients out into something a little looser towards the center of the original faces. Okay, so these are just the initial modifiers. Now the interesting thing really is not just this, but it's actually the fact that, and as you can see here, it's actually the fact that you can modify these, or you can mix and match these one by one successively. So you'll see here, I took the split quads one here, and I stuck a bevel edges, which is under the transform right here. Right? So split quads and then bevel edges. So these are all kind of more or less the same. There's a distance. It takes a mesh. If I turn it on and I'll turn the splits quads off, you'll see it does something crazy like this, right? You can change. So it takes that original, and can't be 0. It takes that sort of original mesh framework of the split quads and actually offsets them and makes a sort of almost like a basket weave mesh framework like this. Okay, so that's the bevel edges. This is the bevel vertices, which is basically the reverse. I make it really large. So if I had these both on at the same time, one is the infill for basically the sort of center portions, right? So sometimes it's actually, to get these to work topologically, if you were going to 3D print something, you would actually need both to get the full weave, or yeah, the sort of full weave or the cage of this. Okay. All right. Then I drop this into a frame. Both of these inputs into a frame. Weaverbird frame, which takes those and actually kind of it's basically an offset, inwards offset. So it's like a picture frame. That's why it's sort of icon looks like that. And the same thing, there's a sort of offset distance. It's this originally as an input, and then as you add the offset, it basically does that, both to this and this, right? So you get a sort of picture framing thing. Last thing here is the Weaverbird thicken, which is actually the equivalent to the mesh offset, where it takes that original input mesh and it gives it a thickness and closes it off as a solid. So this would be a enclosed mesh. You can adjust the thickness, and because it's a mesh, this sort of way of giving things thickness is usually a lot lighter than the NURBS offset. So if you had something this dense that was a NURB surface and you try to do this offset, chances are Rhino would crash. That's just how it is because there's just so much geometry here. Because it's the mesh version, Weaverbird thicken, mesh thicken, it's right here, right? There's also an offset mesh, but the difference is that the offset mesh is an open mesh, right? This one actually gives you a closed solid. So this would be 3D printable, this would just be an offset surface. And so you can see if I bake this, this is actually, let me change this to, right, this is actually one whole mesh. Now, granted, as a 3D print, a lot of this may not survive because you're having these, right, these sort of impossible L joints, right? But you know, you can kind of see the sort of power of using a mesh vertice, a mesh offset logic. Okay. Now, the thing is, in particular, is that we're not actually stuck to only using one of the subdivision modifiers by itself. You can just as easily mix and match them. So I could, for example, if I tone this down a little bit, if I just like copied, let's say, the Catmull Clark and pushed the split quads into it, could just as easily do something like that. Let me delete this so it's not in the way. Okay. And let's do the subdivision iterations independently. Okay. So we know from the original split quads it does this, you know, and maybe that's one iteration, but you can actually push this into a Catmull Clark, for example, that would then take that and do a Catmull Clark to it. So you can actually mix, and you'll see that it gets softened or rounded out a little bit, right? While still kind of having that overall, a little bit of the polygonal faces, although a little bit relaxed, right? Albeit a little bit relaxed. So the main idea here is that actually you can mix and match all of these, right? The sub-D ones. They're easy to sort of work in between. So you can do this the split quads after Catmull Clark, or you can actually do two Catmull Clarks, you know, end to end, whatever. Like you can actually mix and match these, or do a Weaverbird loop after the Catmull Clark. So do this, and I'm just copy pasting these just so you can kind of control individually. So this just kind of just depends on how dense of a mesh you really want to end up with, or how detailed the mesh you want to end up with. And at this point, instead of being quads, now these are triangles. You know, so this is how all of these things work. This is just a very quick sort of example file to show you. You know, oh, these are all things that you can mix and match to get a lot of different crazy configurations. Okay. So mess around with that a little bit just to understand what's happening. There's a sort of brief description for some of these. Loop equals triangular. Some of the transforms. Okay. Now what we're really interested in is actually in this one. The mesh relaxation. There's a Rhino file that comes with it and the Grasshopper file. So I'm going to actually close this. Okay, so this is the mesh relaxation Rhino file. One thing to note is that these are mesh faces. Some of this one's a poly surface, but these are meshes. Okay, just so you know, right? So I'm going to drop in the mesh relaxation, and this kind of gives you an idea of what happens. So this is the Weaverbird loop that we were talking about. These are just mesh boxes. And let's see where here. Okay. This is at the origin point. This is a mesh box. That's from mesh, primitive, mesh box right there. And then you drop one in. X, Y, Z divisions. So how many divisions on each side? You know, you can make it denser, less dense, etc., etc. Okay. So what bearing does that have on this? Well, there are two variables to this. One is, you'll see that the Weaverbird loop subdivision, which is the green thing in the center that we saw before. Let me simplify it a little bit. So you see, as I do more subdivisions, you know, it kind of rounds a corner, you know, it loosens or relaxes things a little bit. It also has a lot to do with like how many divisions are in the original mesh as well. So when this is much higher, so it's a 10 by 10, then this actually kind of doesn't loosen as much or doesn't relax as much. When this is much coarser, let's say, let's do a 3 by 3 cube, then when I go up in my iterations, it kind of pulls away from the surface a lot more, right? But it's just basically the idea of, you know, taking a very simple mesh framework like this, which is, you know, when you kind of come down to it, it's just a 3 by 3 mesh box, nothing really complicated. But then you can get this sort of rounded cube out of it with the Weaverbird loop. Okay, so that's just like the basic fundamental example. Now this is a mesh input. So if you look at these guys, essentially, this was constructed by making a mesh face or a series of mesh faces. You're not probably used to ever drawing mesh faces yourself, but you can actually draw mesh faces for mesh, polygon mesh mesh plane, mesh box, you know, 3D face, which is kind of basically the same as the sort of 3-point plane tool that you sometimes use a lot here. And it can do 4-sided ones as well, basically. Yep. And then the other one is basically the plane, which is a simple plane that has a certain amount of subdivision. Now I could basically draw one that is, you know, when I'm setting this, I can set the XY faces here. So if I set 3 by 3, and you know, I can draw this, then it's almost exactly that, except you would explode this. Well, actually, this one is a mesh face with 9 mesh subdivisions. This one is drawn one by one just to show the process of like getting to this. But this is essentially a mesh grouping that's been joined together. But I can still explode it and into its individual mesh triangles, right? Or you know, if I get a good angle on this, select everything together, I can still join it back together, and it would become a joined mesh. Okay, so these are just meshes, and I'm using that mesh as an input. Now, just like kind of note, the corners are a little bit different. One of them is folding this way, one of them is folding this way, and that's the input, right? Ignore this move. I'm just sort of shifting it over so you can see the results a little bit better. But this is still the Weaverbird loop, right? 0 subdivisions basically is the original. 1, 2, and 3. So you see that sort of simple polygonal mesh yields this sort of result, right? It's actually a sort of complex curvature surface that was derived from that by kind of applying the Weaverbird loop logic. Right? Okay. Now this is because this is an open plane. it's an open mesh with edges. It has naked edges, right? So compared to the first file or the first example, this one actually has an edge, and you actually have some options to deal with those edges, how to treat the naked edges. So 0 is, we'll keep it the same. It won't modify these edges, the naked edges. So keep the same sort of point locations. 1 will kind of smooths it out. So that's why you get this. And then 2 retains the sort of point edges, the ones that are folded like this, but it smooths out the ones that are like this. Right, so I still get these 2 points at the ends. These 2 points at the ends, but I get rounded corners on this one. So that's just the difference. Okay, so that's kind of it applied to a sort of 2D framework. Now the last example we're going to look at here is a version of this. So obviously you can see that you can actually draw your own, let's say, mesh planes or mesh topology structures to kind of work with, in this case in particular, the Weaverbird loop subdivision method. This one, as you can see, is actually about, and I've linked both of these in a simple and a complex version. The simple version is just this, right? It's actually a series of these interconnected boxes with some faces deleted out as a whole poly surface. And it has this sort of continuous topology to it, especially this guy. This guy has this sort of in and out cellular topology to it. This you can always kind of follow, in a way, follow the surface, which yields the results that you see later. Okay, so same thing. Ignore this. I'm just moving these results out of the way. Otherwise, they would be kind of superimposed right there. But basically what I'm doing, I'm taking the B rep and I'm meshing it. So this is under, as you would guess, under the mesh tab, mesh B rep. So you can take a B rep and mesh it, and if you mesh it, then it becomes a mesh, as you would imagine. And under here are settings, and so I'm going here utility to set, and these are kind of some of the setting options. I'm using the quality, which is the smooth setting. This is basically, in the 3D printing sort of tutorial, we saw the left side of a slider and the right side of it, very simple and the very detailed. So this is detailed, this is very simple, and it would give you a mesh that sort of corresponds respectively. So let me hide this really quick so I can show you. Okay, so that's the mesh, right? That's the mesh with smooth setting. You can kind of see. And in this case, it really doesn't matter because our mesh is rectangular anyways, right? These are all flat faces. It doesn't really, the setting doesn't really make a difference. Okay. Pushing it through the Weaverbird loop, same thing, look at this. So it goes from the original one iteration of subdivisions, and this is the loop, so it's making triangles, right, out of those flat faces while keeping all the faces interconnected. Second iteration, third iteration, and now you're getting something that's really interesting as a sort of continuous looping in and out surface. Sort of like a Mobius strip, except, in 3D as a 3D sort of cellular geometry. You can play around with these, but you would get sort of slightly different results. Like these kind of hold the edge for 0. 2 actually doesn't do much because I don't think there are points in this. Wouldn't change. It's not different from the 1. Okay. So it's essentially really easy to understand how this gives you this, because of this sort of smoothing effect. 1, 2, 3. Okay. As a continuous surface, but if you're able to continue it vertically in 3D by alternating these guys, then you can actually construct something really interesting like this. Okay. Now this is somewhat contingent on the mesh face or the sort of poly surface faces being somewhat consistent, both in terms of how they connect. You could probably warp or distort this a little bit to get something a little bit different that has like varying sizes and whatnot. But you would have to stick to some pretty strict rules as far as like making sure the edges are connecting a very specific way, that the sort of topology stays the same for this to work. And then obviously you can do the Weaverbird thickness to give it an offset thickness. As you can see, it's really easy to modify because these are all mesh triangles, and it's a lot less heavier than the equivalent offset of it in NURBS, Rhino NURBS surfaces. So bake it. Let's see. And these are absolutely watertight, fit for 3D printing, full meshes with offsets, with offset thickness that you can specify. Okay, yeah, so that's the sort of mesh relaxation tutorial, and I'll see you in the next one.